So first up, we have Brett Denevi, who will just kind of give us a general overview of lunar regolith. And you can go ahead and take it away, Brett.
Hi, Ryan. Thank you. So I was asked to give a brief overview of the lunar regolith, and I sort of feel like it's my duty to remind you all about how great the regolith is, so that when later today you hear about what a pain all of this dust is, you'll also remember what a rich trove of scientific information we have in the regolith. It is the source of nearly all of our information about the moon, nearly all of our remote sensing information, and it is the source of every sample that we have returned from the moon. And so the regolith contains a rich history, not only of the moon, but of the history of the solar system. And so hopefully you won't think of it as only something to be mitigated. Next slide, please. The most general definition of the regolith, as we already heard from Addie, but it is the layer of fragmental debris that covers a more coherent substrate. That substrate may be bedrock, or it may just be rock that is less fractured and fragmented than the regolith itself. The fragments of the regolith include all sizes, from dust to building-sized boulders, and they can be derived from the rock below or thrown in from very distant impacts. And when we look at it up close, as you can see here in the 125 to 250 micron size fraction of an Apollo 14 sample, we can see this trove of minerals, lithic fragments, breccias, glasses, that all contain their own story of the history of the moon. And then when we zoom out from that sample, to where the landing site, shown with a star at the lower left there, where the landing site lies at the global scale, we can tie these small bits of regolith to the bigger picture of the moon's origin and evolution. Next slide, please. The regolith, of course, is produced by impact events of all sizes. Early on, the big basins produced kilometers of ejecta and the layer of debris known as the megaregolith. And as time progressed and these bigger impacts dwindled, the small impacts took over to produce the fine-grained regolith that covers nearly every surface on the moon. And on the right here, we now know that thermal fatigue is likely to play some role as well, where the extreme temperature cycling of fractures, big rocks, as you can see here with these boulders, these may have been fractured by this temperature cycling and broken them down into the finer grained pieces. Next slide, please. But the regolith doesn't progress neatly from big pieces being broken down into smaller ones. Impact events also create new rocks with their extreme pressures and temperatures, including regolith breccias, such as the extremely friable rocks that were found at Van Serge crater at the Apollo 17 site, pieces of regolith lithified back together into a breccia. And entirely new rock, such as the frozen river of impact melt that you can see in the lower left outside of Tycho crater. And this cycle of creation and destruction continues on with these new rocks being broken down into new regolith in a way that's predictable, so that the abundance of rocks at a crater can be used to estimate its age. Next slide, please. And then with billions of years to develop, the regolith is pretty thick. Many different methods have been used to estimate its thickness, including the active seismic experiment seen here at the Apollo 16 landing site, where 3 mortar shells lobbed explosive charges up to almost a kilometer away to provide an active source in order to probe the structure of the upper 100 meters or so of the surface. And the canonical values of regolith depth are that it's around 3 to 5 meters deep in the Maria or 10 to 12 meters deep in the highlands. But there is some evidence that these are underestimates. Next slide, please. Including ground penetrating radar data from Chang'e 3 and now Chang'e 4 that showed that the regolith may be 4 to 8 times deeper than some of these early methods suggested. So we don't necessarily have to shell the moon anymore. We can just bring GPR to learn about the regolith thickness and structure. Next slide, please. We also have spectacular new information about how the regolith is gardened, how it is turned over and reworked by impact events. You'll hear from Emerson Spiro later, but here you can see a ratio of images from LROC that were taken before and after the formation of a new impact crater. And even though this crater is tiny, it's just 12 meters, it's that little bright bit in the center there, its ejecta has affected the surface nearly 2,000 meters away. So this new knowledge of how the effects of crater ejecta and secondary craters turn over the regolith indicate that it's being gardened at rates of over 100 times faster than previously thought. And then on the right-hand side there, we can see how Emily Costello has taken this new information on the effects of ejecta and secondary cratering and revised an old model from Don Galt to show how gardening generally manifests over time and with depth, going from homogeneous, reworked regolith at the top to fresh material that has not really been disturbed since its emplacement at depth. Next slide, please. Of course, that is a model that captures the broad picture, but regolith is highly variable from location to location, such that the stratigraphy in the regolith is really a unique record of the impact history of that particular spot on the moon. For example, you can see when you look at a drill core from the Apollo 17 landing site that extended down to nearly 3 meters depth. But at this spot, we don't have a mature homogeneous layer at the top, as would be indicated by a high I sub S over FeO value there on the x-axis at the bottom. But we have submature and then extremely immature soils near the surface, possibly related to ejecta placed by secondary craters from the Tycho impact event. So opposite to what would be expected, you then have more mature material lower down, and even at nearly 3 meters depth, there is no immature material. So I would love to see cores on future missions that extend to much greater depth to get at that lower regolith, layers of paleo regolith, and then pair that with ground penetrating radar for context. Next slide, please.
About 8 minutes.
Thank you. Later today, we will hear more about space weathering, but you can't really talk about the regolith without at least mentioning the really profound ways in which it is affected by the space environment. The beautiful fresh rays of craters like this one that will slowly fade away until they match the darker, mature background due to these processes known as space weathering. Next slide. And these processes alter the surfaces of soil grains so that they have rims that contain tiny bits of metallic iron, and micrometeorite impacts turn usually about half of the soil into agglutinates, which are these glassy, irregular particles that also contain bits of metallic iron. And these changes really strongly affect our remote sensing data of the moon from the UV out into the thermal infrared, which you'll hear more about from Jeff Gillis-Davis later today. And last slide. So finally, we were asked to name a couple of our top regolith questions, as Ryan mentioned. And so these were mine. First, what lunar and solar system history is contained in the feldspathic highlands terrain, regolith, paleoregolith, and megaregolith? I think there's still a lot of surprises there. And then next, what will we learn from the poles? How does space weathering manifest itself at the lunar poles? And then how do volatiles migrate through the lunar regolith? So I will leave those there. Thank you.
Great, thanks, Brett.